Yeah, we can wait for 1 or 2 minutes, or you could just simply start saying something. And,
yeah, I mean, let me just share the guidelines. So before we start.
Well, I think it's not really necessary, Bindu, because I think there are so. I mean, we have just sent it by email, and people already know. Don't. Thanks. Yeah. It will probably scare away people then.
Okay. Yeah, so everybody knows the guidelines. Yeah.
How do I share the screen if I have to?
You're the co-host, so you should have an option at the bottom of the screen.
Yeah, I do, but let me try. Shall I try doing it?
Yeah, you can share your screen. Yeah.
But somehow, is it showing? Can you see it?
Not yet. You have started sharing?
Yeah, I've tried to. So maybe Ian can explain. So I think last time I gave the talk again, I did the same exact thing.
Okay.
Well,
yeah, I just clicked share screen. Yeah, there's a green button, right? Share screen, and then you select
that. Okay, now it's coming. Okay, that's good. All right.
Okay, yeah.
Can you see the screen?
Yeah.
Okay.
Okay, yeah. So, will we start, Ian? Yeah.
Yeah. You should make the decision, Bindu. Yes, of course.
Yeah. Okay. So, welcome everyone to the evening session of this wonderful conference. And so now our speaker, the first speaker is Chethan Krishnan. He's from Indian Institute of Science, Bangalore, and he's going to tell us about cosmic censorship of Trans-Planckian field ranges in gravitational collapse. Okay, so over to you, Chethan.
Okay, thanks, Bindu sir. Let me start by thanking Suresh and Ian and Tanay for organizing this conference and letting me speak here. And it's a pleasure for me to be back in IIT virtually, after a long time. So I'm going to talk about this paper that we put out recently with my undergraduate student who's recently graduated and is leaving for Caltech now. He did the heavy lifting in this paper. I should start by saying that. And so there is a little bit of a history. He wanted to do numerical relativity, and I'm not a numerical relativist at all. So, but I'm the closest thing that he could find in our department. So he came and asked me for a problem, and that's how we started doing this. So okay, so we got some help from this gentleman Junki Guo in the process of this work. And so it's also, there is some work that I'm doing with my PhD student, which is not yet out, which is also kind of part of this. Okay, so the question that the context of our question is very old, which is about gravitational collapse, and it's a very old subject. And but this question of gravitational collapse is usually phrased in terms of perfect fluid sources, by which I mean things like dust spheres or shells or things like that. And the oldest example, I mean, maybe not the oldest, but a fairly conclusive result was already known in 1930s, and that was done by Oppenheimer and Snyder for a dust ball collapse. So the context in which usually gravitational collapse is addressed is in the context of collapsing matter, as being fully determined by a conservation law for the stress tensor. So perfect fluid basically means that you're not looking at the field theory underlying the system. You're looking at a stress tensor, a perfect fluid stress tensor with some particular equation of state, and that's the source for gravity. So we ignore the underlying field theory dynamics. And one practical reason why this is done is because many times we would like to study a collapse sort of quasi-analytically. And if that is the case, it's better to aim for an ODE rather than a PDE. And this is a practical reason why this might be a useful thing to do. And even if the system is spherically symmetric, if you allow smooth spatial variations during collapse, you will be forced to work with PDEs because you'll have both an R and T dependence in the system. So what these fluid shells and spheres often do in practical terms is that it translates this collapse problem into a question about just tracking the surface of the shell. So you have a spherical shell and it's basically just some function R of some suitable time T, which can be a proper time on the shell or something like that. And this is what you're trying to, so the problem you're trying to set up is a problem for this R of T as a differential equation. And then this is manifestly an ODE, and which you can, in principle, try to understand something quite easily. So this is one practical utility of looking at this. At the price you pay for this is that you introduce a discontinuity at the surface, at the shell surface, as a proxy for these spatial variations. So for instance, a dust sphere of Oppenheimer-Snyder or the null shell of Vaidya and company, all of these things, all of these setups basically have are essentially some radius of some shell or some surface that you're trying to track. So, and discontinuities in fluids are not unreasonable because, for example, stars have surfaces. And a fundamental way to understand, a basic way in which one can think about this is that a fluid discontinuity is simply a variation that happens over a length scale that is small compared to, let's say, the size of the star, but is large compared to the ultraviolet cutoff of your underlying theory, which you can, if you're working with a weakly coupled fluid, you can think of it as a mean free path. So, and that's a reasonable thing to do. And that's why this approximation is a reasonable one to do at the level of a fluid. But on the other hand, if you're working with a field theory, it's less clear whether it is okay to have discontinuities explicitly in your system, because if you have two derivative theory or scalar field or something like that, this is a discontinuity. And so in some sense, you have to keep track of, so there are many reasons why it is may not be a reasonable thing to do. And so if you're working with fields like scalar fields as sources for gravitational collapse, then you want to allow the possibility that these fields are functions of both R and T, and then you're immediately dealing with partial differential equations, which have to be explicitly solved in some computer or something like that. And this is not very amenable to intuition, and there are surprises. So this is the context in some sense. So we are trying to look at scalar fields as sources for gravity and how they're going to affect the evolution of these collapsing systems. So, and the surprises, one particular surprise that was noted, I think probably in the 80s, was by Choptwick, and this is a well-known and famous example, where he studied the classical gravitational collapse of a massless scalar. For simplicity, I think people so there are people have extended it to other situations with massive and with cosmological constant. All kinds of generalizations have been done. So the original situation was a massless scalar being a source for Einstein's gravity. And the motivation for doing this was initially the fact that there was a theorem which was proved by Christodoulou long ago, a while ago, which was that Minkowski space is stable to small perturbations for some finite radius of convergence of the perturbation. So then there was a natural question whether how much do you have to perturb Minkowski space before you start producing black holes? So, and this question was what Choptwick was motivated by. And so what he showed was that there exists a finite value in the space of initial parameters that you can have for the scalar field profile, after which you start creating collapse and horizons. And at the transition between dispersal and collapse, you end up finding a naked singularity. And you also end up finding that there are critical phenomena. For instance, the mass scales as a power of the difference between the controlling parameter and the value of the critical parameter to some power. So much of this doesn't really matter for my discussion. I just wanted to say that there is, so the context in which optic worked, you identified critical phenomena at the boundary between dispersal and collapse, and that was the punchline. And this was not something that one could have anticipated by looking at just the equations at an analytical level, and this really required. This is one of the interesting results in general relativity, which I think is essentially completely inaccessible without numerics. So, oh yeah, and also if you have any questions, please feel free to interrupt. And so at any point. So in fact, if you have any questions, I can pause for a second and take questions. This is just the introductory part. Okay, so my motivation for considering the same system is that is in the context of the swampland program, and swampland conjectures try to identify conditions that must hold in effective field theories if they are to admit ultraviolet completion when you couple it to gravity. So we'll be concerned with specifically with the swampland distance conjecture, which I will explain in the next slide. So this is the context. So we would like to understand what happens to the scalar field during gravitational collapse. Okay, so swampland distance conjecture is a statement that given an effective field theory action that contains gravity and scalars, there is an order 1 range in the scalar field space for which that action is valid. So here order 1, everything is in Planck units. So so the field range that the theory is trustable is order 1 in Planck units. So beyond that, the tower of light particles in the ultraviolet become light, and your theory, so your low energy effective field theory is no longer reliable, and you'll have to resort to some other way of describing the system. So in other words, if a solution of effective action has movement of scalar beyond an order 1 range, then this swampland distance conjecture would imply that the solution is not reliable in those regions. Okay, so I will mostly be concerned with one particular argument that is usually made for why the scalar field ranges are supposed to be less than order 1 in an effective field theory if it is a theory of gravity. So, and this is usually attributed to Banks, but even though I have not been able to find a very clear reference on it. So the idea is that if let's say scalar undergo a movement by delta phi, so some field range within a length scale of order L in some space-time. So the idea is that the scalar field value changes by delta phi within a length scale of L in some space-time, and then the energy contained in this region would go as like this. And the idea here is that so this is just the gradient energy, and this is the volume. So that explains how much energy is stored in that region if the scalar field is changing. So from the Schwarzschild metric in higher dimensions, we expect that if the energy contained in some region satisfies this relation here, it will basically form a black hole. So this is just the Schwarzschild metric, just looking at the Schwarzschild metric. And for the scalar field excursion above, this happens precisely when delta phi is order 1. So, and the interesting thing about this is that no matter how fast or slow the scalar field varies, that is, doesn't matter how much, this does not depend on L. So doesn't matter how, even if it is fast or slow, if the scalar field moves by order 1, it will form a black hole. And for various reasons, you can argue that this is a bad thing if you want to look at it from some asymptotic region or something like that. So that's usually presented as an argument for why an order 1 field range is expected in a more than an order 1 field range is somehow problematic in a theory of gravity. Okay, so these arguments, the variations of these arguments have appeared in many of these papers, at least the ones that I've been able to find. And our goal in this talk will be to reverse this logic and consider classical gravitational collapse sourced by fields. So our goal is to understand what kind of field ranges one can expect in gravitational collapse. So in the heuristic argument that I just outlined, the order 1 field range is essentially put in by hand, in the sense that it is, okay, if there is an order 1 field range, then what do you expect to happen? So here, on the other hand, what I'm kind of looking at is what happens if you take into account actual dynamics, and what can you say about the system. So what happens if your source for gravity is a scalar field? Okay. So what we'll do is we'll consider Choptwick system, by which mean just the Einstein scalar system, and numerically evolve these equations. So, and Choptwick considered a 1-parameter family of scalar field profiles, as I mentioned, and identified the critical value of this parameter at which configuration resulted in collapse as opposed to dispersal. Our goal is not that, is not directly that. We are not particularly concerned with the precise location of criticality in the parameter space. We are primarily interested in the supercritical cases where we are actually going to form black holes. So, so what we are concerned with is the situation where you're in some sense less demanding from a numerical relativity point of view, because if you want to really understand the critical behavior at the transition from dispersal to collapse, you really have to make sure that your evolution is, there is a tremendous amount of precision required, especially for tracking the late time evolution. So yeah, so so our field will be a scalar evolution in the systems, in the sense that the metric itself is of secondary significance to us, because we would like to know how much the scalar field evolves when collapse happens. And we'll find that in near critical and supercritical collapse scenarios, these massless scalar fields move by an order 1 field range. So, and this result seems to be quite robust as we vary the shape and the parameters of this initial scalar profile. So this is the punchline. I'm telling you the punchline, and I'll go into some detail, but not much, about this thing, about how we get it, etc. And so the second point is that, the second observation is that we also find strong evidence that in every supercritical situation where the field moves by order 1, the large field range is in fact covered up by an apparent horizon. So since apparent horizons are known to be inside or coincident with event horizons, this should be viewed as a type of cosmic censorship for the Trans-Planckian field range. So it's somehow it's the converse of the heuristic argument that I made, which is that if the scalar field is what is sourcing the collapse, then you find that the field does move by order 1, and we also find that the field range is actually covered up by an apparent horizon, at least in all the cases. Of course, all of what I'm saying is based on numerical experimentation, and yeah, so it's not entirely clear whether it is 100% watertight, but in all the cases that we have checked, and it seems like it is holding. Okay, so the system that I'm looking at is basically just the simplest thing that you can imagine, which is Einstein gravity coupled to a massless scalar. And the metric that I'm working with is in a standard form that numerical relativists work with, which is there are 2 functions, sigma and r. And let me emphasize that r is not a coordinate, it's a function of t comma x, where t and x are the actual time and spatial coordinates on this in this geometry. So the 3 independent guys that we have are phi and sigma and r, and the combined evolution of this system is what I am really concerned with. Okay, so yeah, so also just to make a note, so the profiles that I will consider for scalar fields, there will be many profiles. So I'm just showing you one example here, just to emphasize that there are a few parameters inside them, like a, the amplitude, x naught is the radius of some shell-like thing, and delta is what the thickness of the shell, for example, if I'm picking a Gaussian profile. So we have tested it for 3 or 4 different profiles, and they all seem to kind of generally follow the same structure, same story. So what I will do is, in this talk, I'll just mention the Gaussian profile, but what I'm saying is generally true for other profiles that we have tested as well. And to evolve the system, it is useful to define quantity m, which is defined like this. And the practical reason why it is useful to define this extra variable is because it just makes it's an experimental fact, and I don't have a deep understanding why, but it just so happens that if you work with these 4 variables, the numerical integration happens to be more stable. Okay, and so instead of working with 3 variables, I'll also introduce this m and then write an equation in a particular form which involves all 4 of them, and that's what you get. So that's the system that we're evolving. And Einstein's equations basically split into constraints and dynamics, and we choose initial data that is consistent with the constraints and then just evolve it. And yeah, so checking constraints at each integration step serves as a sanity check, and of course we want to keep it below some threshold. So this is the way we are doing it, and this is very standard. And yeah, so the features we are after are quite robust features of the evolution. So as we will see, so they are, we see it essentially in every situation that we have tried to evolve. So unlike the vicinity of the critical naked singularity that Choptuk was interested in, so our problem is fairly easy by numerical relativity standards. And as I should also say that I feel confident, or I think that it's almost inevitable that people who have looked at numerical relativity, when they were looking at supercritical cases, they must have, if not seen it, at least they would have seen similar results, even though their focus was probably not on this particular fact of how much the scalar field is running. So the way we find it, at least it seems an extremely robust fact. So yeah, so I also should emphasize again that in this evolution we got substantial clarification from a numerical relativist, and his help was really useful for us to do our stuff, get confidence in our results. Okay, so I'll just flash you one slide of the actual plot of what this thing is. So here what I'm plotting is the value of the function at x equal to 0, of what value of the scalar field at x equal to 0 for a specific Gaussian profile with some specific choice of parameters. Well, I mean, 2 specific choices of parameters, one of them which is subcritical, which is shown in blue, and another one which is supercritical, which is in red. And as you can see, the scalar field value moves by more than order 1 when you're supercritical. So this is a time plot of the value of the field at x equal to 0. Okay, so right. So I think, yeah, so I think that's, so this is basically, you can see that we have stopped plotting at some particular point, but in principle you can go further, and you can see that the scalar field range is order 1. And in fact, the psi is actually the scalar field divided by a factor of square root of 8 pi. So this is definitely more than order 1. Okay, so so yeah, so this is another case which is supercritical and where there is collapse, and we are just plotting the scalar profiles as a function of time. Blue is the initial profile, and red is a late time profile. And you can again see that the profiles gradually, as time goes, it keeps moving, and you can see the sort of the time snapshots of these profiles at various times. And this is again a Gaussian profile with some particular choice of values. Okay. So again, any questions? Is anybody there? Can you hear me?
You're all here.
Yes, we can hear you.
Okay, good. So okay, so yeah, so the second point is that censorship of Trans-Planckian field ranges, by which I mean, yeah, so this is the second piece of the observation. And so this is another place where defining this Meissner-Sharp mass, this mass quantity is useful, because one can show that this parent-Riet equation just reduces to the simple form. And in fact, that's one of the motivations for defining the Meissner-Sharp mass in this particular way. And this equation has to be, so yeah, so of course, since our solutions are numerical, this equation has to be solved numerically using the solutions we have constructed. And this R is a function of the radial-like coordinate x and t. And it turns out that in every case that we have checked, right as the field starts moving wildly, an apparent Riet forms right around it. So this is another numerical observation. And I will just flash you one slide. So there is some, yeah, so So the point here is that this is a scalar profile for a collapsing case or a supercritical case where right after the large field movement has commenced, and the vertical line is the location of the apparent horizon when it first appears. So you might see that. So you might see that there are two lines here actually, and that's because this equation that I flashed you here actually has two branches of solutions, and one of them goes inward as time evolves, but the other one stays outside, and this outer one is what one calls the true apparent horizon. And you can see that you can see, and it's always the case that the large scalar field range is always inside the outer apparent horizon. So, and one more thing I want to say is that we completely missed this in the first version of our paper. When we first wrote the first version of the paper, we just wrote the first part, which was about the order one field range, and just left it at that. And in fact, it was during Himanshu's thesis that we recognized that, oh, maybe we should consider this, where exactly is the horizon? Maybe that is interesting. And that's when we revised the V2, and we found that indeed, in all the cases that we could find, the field range actually is inside the apparent horizon. So yeah, and so one of the reasons why we actually looked at the apparent horizon in the first round also, but the thing was, as I said, there are two branches to the two branches of solutions to this guy, and if you're not looking at the right branch, it doesn't look very interesting. So if you really have to look at the outer branch specifically to really realize that all through the evolution after the scalar field has moved by order one, the apparent horizon is always outside it. Yeah, so let me add some caveats to the statement. So when the collapse is very close to criticality, it is harder to separate the field movement from the horizon and the singularity. All of those scales overlap with each other because you're really dealing with the naked singularity. But this is not very surprising. So critical collapse is the boundary between collapse and dispersal, and so it's a violation. So what we are finding is something that has at least a spirit of cosmic censorship, in the sense that there is a large field range which is actually getting censored by a horizon. So, and in that sense, just as the usual cosmic censorship is in tension at the naked singularity that is at the boundary between dispersal and collapse, we also expect this censorship also to be not particularly well defined at that transition. So indeed, we find that the closer we are working with the criticality point, the more and more of the order one field range seems to be, well, not too much actually, but a little bit of, let's say an order one fraction of the order one field range can lie outside the outer horizon, the outer apparent horizon. So, but I don't think that violates the concept, so to speak. Okay, and so the reason being that this is a highly non-generic situation, because to reach it requires fine-tuning in the initial data. So if you really have to fine-tune the initial data in order to get to the critical point, critical collapse. So, and it is known that anyway cosmic censorship is violated by a naked singularity. So since our observation above has the flavor of cosmic censorship, it is therefore unsurprising that we should see some inessential caveats when we are close to criticality. So this is basically what I just said. Okay, so let me. So this is basically all I had to say. I mean, it's really a short talk. So just two observations, and they're kind of simple observations. So our results suggest that scalar field ranges may be a useful indicator for effective field theory breakdown inside the horizon for scalar field collapse. So this should be contrasted with the usual indicators such as breakdown, namely the divergence of curvature scalars and tidal forces and such. And this is a sort of a converse of the heuristic black hole argument that we started with regarding swampland field distances. And I should also probably mention that it has previously been noted that cosmic censorship and weak gravity conjecture are closely related by a bunch of people, Santos and many others, a few other collaborators of his, where they find that there exist scenarios where you can find, you can create naked singularities in a reasonably, I would say in a perfectly reasonable context, as long as as long as you're willing to violate the weak gravity conjecture. And they find that if you add particles which do saturate the weak gravity conjecture, then you actually do not find this naked singularity. So there is some similarity to that here, and so maybe one can ask the question: what class of swampland violations of effective field theory can be hidden behind horizons? And yeah, so I should also mention this some papers by Draper, which I found kind of somehow to be somewhat they were kind of thought-provoking. So, but I don't have anything much to say about it. They are working with static scenarios. We are working with dynamical collapse. So yeah, that's that. So let me conclude with some speculations. Firstly, we expect that working with non-canonical kinetic terms or more number of fields will also lead to a violation of the swampland distance bound in the same way that I discussed here, but the difference being that the field space distance should be the invariant field space distance defined in terms of the appropriate field space metric. And a second point worthy of further understanding is the question of adding potentials to scalars. So we have done some numerical experimentation with massive scalars, and it didn't look like the claim statement was changing. So I think it is natural that even in these cases, the scalar field probably does move by an order one range if you have when collapse happens. So, and thirdly, and perhaps more interestingly, yeah, so this is I don't have a very precise statement yet. So when you have this kind of scenario where the Trans-Planckian movement of the scalar is happening, when it is getting censored by the horizon, we often find that the field movement actually happens pretty close to the horizon. So there are some questions about the coordinate dependence of the statement, which is why I don't want to make a very strong statement. But it looks like at the moment that the field variation is happening closer to the horizon than to the origin of the spacetime of x equal to 0. So which maybe is a suggestion to understand where exactly is effective field theory breaking down inside the interior of the black hole. Because if you believe classical general relativity, you find that the breakdown is happening at the origin, and it will be interesting to precisely translate this kind of a statement into a statement about breakdown of effective field theory due to this swampland distance bound violation. So yeah, so this is what I was just saying. So preliminary evidence seems to suggest that for large black holes, the Trans-Planckian field ranges happen inside, but closer to the horizon than to x is equal to 0. So this might be thought of as a hint of some kind of a firewall. So yeah, but that is still kind of preliminary. Yeah, so another comment that might be worth making is a scalar range is a non-locally measured quantity in space-time, whereas high curvatures are local. Can this be put to some use in understanding the role of EFT in the black hole interior? So that's that. And yeah, so and I also should make one more comment, which is that our numerics as the black holes gets bigger and bigger, it's harder for us to do our numerics. So it's a little bit difficult to really separate this out. And somebody who actually knows what numerical relativity is might actually be able to make better use of these kinds of things. Okay, so finally, to summarize, the takeoff message is that in near critical and supercritical collapse scenarios, the massless scalar field moves by an order 1 field range. And in every supercritical situation where the field moves by order 1, the large field range is in fact covered up by the parent horizon. So this is the statements that I made earlier. And that's all I have to say. Thank you.
Okay. So let's thank Chethan for this nice talk. Okay, so we can take questions from the audience.
I have a question. Very nice talk. So the distance conjecture suggests the way you applied it to field range that near the singularity of the black hole, where it breaks down, and so effective field theory should break down there, presumably suggesting that there are dual description takes over, right? So you mentioned firewall. Why would you say firewall instead of a dual description?
Yeah, no, so, in fact, yeah, I agree with you. So it's depends on what your prejudice is. That's what I mean by that statement is that if you think of firewall as a breakdown of effective field theory, then that's a firewall. But it's maybe one effective field theory to another. So maybe there's a duality or something like that, which translates.
Complete description of that's like what we always see, that when you go to extreme parameters, the complete description is impossible within one Einstein description, and you need a dual description. And that's what apparently might be a resolution natural resolution, I would say, what's happening near
Yeah.
the singularity.
No, yeah. So yeah, I mean, So yeah, by firewall, I just meant that it's a breakdown of effective field theory in one description. That's really what I meant. Yeah.
That's very nice. And the other thing is that you mentioned you also studied the case with potential.
Well, we did not really study it. We did some evolutions with masses, and still we found, but those are like very sporadic, a few cases.
So my question is actually, could you extend this to the case where you can see whether or not there's any relation between this and the slope conjectures on the potential?
Well, I have not really thought about it, but yeah, I think, yeah, so certainly it's something worth thinking about. Yeah, I don't have a comment about it. Yeah. Yeah.
Okay, thanks. Nice talk.
Thank you.
Any more questions?
Yeah, can I ask one? Yeah, Chethan?
Yeah, sure.
Hello?
Yeah.
Yeah, so I was just wondering if the profile that you had for the scalar field with those local maxima have something to do with the turning points that one would see in the case of, Einstein fluid systems, for example, where they transition from stable to unstable.
I don't know what is the turning point. What do you mean by turning point?
Yeah, so like there are these things where you plot mass versus, let's say, radius in the case of in the case of a fluid on a curve value, and I mean, you'll find these local maxima, which I think they were studied by Wheeler.
I'm sorry.
The mass of the system.
Talking about. I'm sorry.
The mass of the system as a function of R.
Oh, I see. Okay.
And I think these were studied by Wheeler and Zeldovich.
Okay.
And so basically in these cases, you'd find that these local maxima correspond to like turning points. So, I mean, each of these maxima would correspond to like neutron star formation or white dwarfs or, that kind of thing.
Yeah.
So is there a similar
yeah. So, but the thing is, yeah.
that?
So I think that, I think that what we are working with is more like the fundamental description. Right. So it's like here it would be more like a kind of a condensate rather than something like a neutron star or something like that. So because it's a scalar field.
Yeah, I got that. I'm just like, I mean, since those things, those maxima correspond to like transitions from stable to unstable, that might parallel with like things about these questions on firewalls and things that you're trying to
I see. The thing is, I would say that this is already past the stability point. That's why the collapse is happening here. Right. It's not like
okay.
So there there is some sort of a tension between some sort of a balancing between two conflicting or competing effects, and then something takes over, and then the instability kicks in. But here we are always from the get-go we are in an unstable situation.
Okay.
So it's we are always in collapse. So yeah, that's so I don't. I mean. Yeah, maybe there is some way to connect it, but yeah, I mean, since also because as I said, I'm not super familiar with what you're talking about, so don't have a very interesting answer.
Okay. Any more questions? Okay, so if there are no more questions, let's thank Chethan once again.
Let me try to.
Yeah. You can start sharing.
I'm trying to. Okay, yeah, I found the stop share. I always forget this. Sorry.
Yeah. Okay, so I think, yeah, so we have the first talk went quite well and we are early on time. So Tim can share your screen. Okay, so welcome to the second talk. Our speaker is Timm Wrase from Laheyk University, and he's going to tell us about misaligned SUSY in string theory. So over to you, Tim.
Yeah, thank you very much for the introduction, and let me also thank the organizers, Suresh, Aryan, and Tanay for putting this workshop together and bringing us all together in this time where it's very difficult or impossible to travel. So I have to, I have to apologize. This is kind of a new topic. I haven't spoken about it before. So this talk might not be like perfect. It might not have all the references, but I hope it nevertheless is very accessible. And I personally think it's a very interesting topic, but it is like 25 years old. And for that reason, some people might be already familiar with some aspects of that. So if that is the case, I apologize because my talk is somewhat introductory. But I hope for people that are not familiar with it, this will be a nice overview and very useful. So this is kind of work done in collaboration with Nicolo, Susha, and Flavio. And Nicolo and Flavio are also applying for postdocs. They are really great, and they have done a lot of the heavy lifting and the calculations in this work. And they also have done many other things. So keep out an eye for their names if you're looking for postdocs. Okay, so what I'm going to talk about is misaligned SUSY in string theory. And I split it up into some vague introduction in SUSY breaking and string theory, why I think this is important and why I think this is something people should look at, and people are looking at it, of course, and have been looking at it. But I'm interested in a particular aspect which goes by the name of misaligned or asymptotic supersymmetry. And I will tell you what that is. And I will also mention a little bit of progress we made when we worked on that. And I think it's useful, hopefully, in the future. So one motivation is simply phenomenology. So CERN has obtained a lot of results, has done a spectacular job at confirming the standard model of particle physics. Unfortunately, there's nothing new. I mean, there was only the Higgs, but we kind of expected that. So there's no discovery of supersymmetry. And that means we are kind of faced with two problems. So we always have been faced with a cosmological constant problem. Couldn't have been really solved by supersymmetry, but at least the hierarchy problem could have been. And one could have asked, why did this not happen? I don't know. But as string theorists, we have some theory of quantum gravity, so we can try to understand non-supersymmetric strings, and we can see whether hierarchies can exist. What do we have to say about the cosmological constant? I think their string theory already said a lot in terms of the landscape. If there's one solution, there should be many, 10 to the 500, 10 to the 272,000, certainly a large number, and that could potentially solve the cosmological constant problem, but that would leave us with a hierarchy problem. I'm not a phenomenologist, but people are applying this misaligned SUSY to the hierarchy problem. So I'm more interested in landscape swampland string compactifications. And there, I think it's fair to say we much better understand the supersymmetric aspects, right? That then when we have sufficient amount of supersymmetry, we can really make very rigorous statements like about the size of the gauge groups, or like in 10 dimensions, we find some string universality where low energy effective theories can come from string theories, and similar things might happen for lower dimensions. That works well if you have sufficient amount of SUSY. For the standard model, and in particular the theta vacuum and all these things, dark energy, things become much more complicated because there's no supersymmetry, and then the conjectures are more speculative and more debated. And that, I think, is where we can hopefully make more progress by understanding non-supersymmetric string theories better, and that is kind of the big context where I see my work right now. Okay, so if you want to have in string theory no supersymmetry, then you have a variety of options. The first one is you just take a non-supersymmetric string theory. That is one I will pursue and discuss a little bit here. The second one is you can compactify a superstring on a space that does not preserve supersymmetry. There was some recent interesting work by Bobby Asharia and many other people. I will not discuss that. I just found it interesting. I mean, naively, you think there's an infinite number of non-supersymmetry preserving spaces. It should be a much larger class than Calabi-Yau compactification or compactification on spaces with special holonomy. But then these people found in certain cases there are instabilities. So the the non-supersymmetric compactifications might not all be stable, and then it's unclear what the outcome really is. Another path, which I and many other people have followed, you just compactify on a supersymmetric space like a Calabi-Yau manifold or a special SU3 structure manifold, and then you have a low energy effective theory in 4 dimensions that preserves some SUSY, and then somehow you break SUSY. And there I would like to distinguish between, I have a standard low energy effective field theory with a non-zero F term or something like this that breaks SUSY, or I do something more strongly kind of like KKLT, where I put non-supersymmetric branes that in principle break SUSY at a potentially warped down string scale. And I've been working in particular on the non-supersymmetric branes. And what we realized recently when, well, already a year, more than a year ago, when Susa was visiting, there is some connection between non-supersymmetric branes and features of real non-supersymmetric string theories. So I'm not gonna like solve all the big problems, but I want to ask some very basic questions that I think are not covered in a string theory course. So I put them here in the introduction and just go over them very quickly. So there are a variety of non-supersymmetric string theories that don't have tachyons. So the bosonic string has tachyons. Those theories are unstable. I'm not really talking about those. There are non-supersymmetric tachyon-free string theories, like for example, SO16 heterotic string. There are a couple of others. And since string theory is expected to be a UV complete theory that gives finite answers to scattering amplitudes or whatever you calculate, you can ask very simple questions like the cosmological constant. Normally they're bosons and fermions. In supersymmetric theories, they cancel, similar with scalar masses like the Higgs mass or something. How would that work in string theory? As string theory, we have a UV complete theory. We kind of understand the spectrum. How can we get possibly here a finite answer? If you tell that to a field theorist, he says, I have no idea. He just says there's a certain cutoff and it should diverge if you send that to infinity. But in string theory, that's not what's happening. So the question is, why do we obtain finite, potentially non-zero answers in non-supersymmetric string theories? I'm not necessarily aiming for 10 to the minus 120 for the cosmological constant, but why is it even finite? Why is it not infinite? And then the question is, could this provide insights maybe for the cosmological constant problem, or at least for the hierarchy problem? And the answer is yes, maybe it could. So that in that sense, non-supersymmetric string theories are very interesting, and I'm just getting into it, but I find it very exciting, and hopefully you will share my excitement. So this brings me to misaligned supersymmetry or asymptotic supersymmetry. I think it goes back to Keith Denis and Kutasov-Seiberg. So in this talk, I will just ask a very simple question, and one can extend it to scalar masses, but I for now just look at the cosmological constant. So if you calculate the one loop correction, which I have drawn already before, to the cosmological constant, you find essentially bosons and fermions contribute with opposite sign, and somehow this should diverge, maybe like the cutoff to the fourth power. So in order for that ever to be finite, it seems we clearly need bosons and fermions. In string theory, if you do this similar calculation, you sum here over the states, but the number of states, you have infinite towers of ever-growing states, and I will make it more precise, but I will not necessarily put in all the exact factors. But in string theory, certainly we have to send the cutoff to infinity to include the infinite spectrum of string states. And in string theory, there will be some regulator in here. It's not overly crucial, so I don't put it in, but it comes out naturally in string theory. If you calculate the one loop cosmological constant, there's a regulator that somehow regulates it. That doesn't help, and that doesn't give you always a finite answer or something like this. There's more going on. So it's not crucial to have the regulator precisely in there. So in string theory, if we want to do something like this one loop cosmological constant, essentially we just need to know the states and whether they are bosons and fermions. And if you take a string theory class, usually you know how to calculate the spectrum. And it turns out all string theories that do not have a tachyon, they have bosons and fermions. So the bosonic string is only consistent of bosons, but it has a tachyon. The SO16 stem SO16 string has bosons and fermions, but no supersymmetry. So all strings that have no supersymmetry and are without a tachyon in the spectrum, a physical tachyon, they have bosons and fermions. And similar to all the supersymmetric strings that people do in textbooks in string theory, we can simply count the number of bosons minus fermions. We can actually count the partition function where we weigh them by the mass. So the one loop partition function in a heterotic string or a type 2 string or whatever, it consists of a left moving sector and a right moving sector, and I have set them already equal for level matching purposes. So I just want to show the partition function essentially counts via this ANN the number of bosons minus fermions with a particular mass mn squared, which is n times the string scale. So here's an infinite tower of states in the partition function, and we can calculate that for non-supersymmetric strings similarly as for supersymmetric strings. For supersymmetric strings, the number of bosons and fermions at each n level are equal. So a and n is 0. That means the partition function is 0. So this is an exercise in I think, List Tyson string theory book or many other string theory books. You just calculate the partition function of any supersymmetric string, and you find that exactly you obtain 0 after using some identities. This is not the case for non-supersymmetric string theories. So how do we connect this partition function to the one loop cosmological constant? To do that, in principle, again, I will not be overly precise. There is a prefactor that depends on the imaginary part of tau2, and in principle, we have to integrate the partition function over the fundamental domain. So the fundamental keyhole domain splits up in an integral over real part of tau and imaginary part of tau. And the real part does the level matching, which I have already imposed. So, and the imaginary part of tau gets essentially a contribution from im tau goes to 0, which you can relate if you want to via SL to Z to im tau goes to infinity. But yeah, I mean, the crucial point is that the cosmological constant is contained in this limit where im tau goes to 0, and then all tau is 0, and q bar become 1. So then you simply sum over a and n, and a and n contain boson minus fermion at each level. So schematically, if I take the limit im tau goes to 0, I find the sum over a and n, which is the sum over minus 1 to the f. So essentially, this one loop partition function that we can easily calculate in string theory, it contains the answer to the one loop cosmological constant. There are some prefactors, again, not crucial for anything for our analysis. So this question of the cosmological constant at one loop was originally studied by Kutasov, Seiberg, and Keith Dennis and others in 95, 94, 91. And in particular, Keith, he writes very nice papers. I like his introductions. His introductions are like 10, 15 pages, but he is like very pedagogical, very nice, gives simple examples, explains everything, and ties everything nicely together. So just the introductions are always very nice overviews, I think, of the whole topic. So if my talk is a little bit too fast or something is unclear and you don't really want to get into the depth of this, just read a little bit of the introduction and it's really fun. So let's look at a concrete example. I always like examples. The SO16 non-supersymmetric string theory has a partition function, sum over a n q n n, which goes like minus 2,112 plus 147,456 q bar minus blah, 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 plus blah, blah, blah. So we see the partition function is not 0. If you're a low energy guy below the string scale, you would say there are some bosons and fermions that cancel in such a way that I'm left with 2,112 fermionic states. So you clearly find things are kind of diverging here. There's no cancellation between bosons and fermions. And there will be no cancellation at any mass level. It's not asymptotically that this goes to zero, this actually grows exponentially. So things become larger and larger. You cannot add these up in any way to get a net cancellation. And the positive I will often refer to as bosons, although they are bosons minus fermions, and the negative ones are fermions, minus fermions plus bosons. Okay, so here is actually a plot of this spectrum. So here's the massless level, then here is the string mass, and then 2 string masses or whatever, 3 string masses, 4 string masses, and so on. And you see there is a very fascinating oscillation. So I said before, all of these theories have bosons and fermions in their spectrum, but it actually turns out there's more. The fermions sometimes, there are more fermions than bosons, and sometimes there are more bosons than fermions. It doesn't need to oscillate that perfectly. It can oscillate in a more complicated pattern, but it always oscillates above 0 and below 0, above 0 and below 0. And intuitively, then it becomes clear how this could potentially lead to a finite answer. So this was kind of the insight from Keith and others that while the bosons and the fermions, they never cancel in these non-supersymmetric string theories at any mass level, they can average out via these oscillations. However, to make that precise is incredibly subtle. To get such a cancellation, in particular from a low energy effective field theory point of view, it seems totally crazy, right? If you ask any low energy effective guy, he said, okay, for each fermion, throw in some bosons. That's what we know from supersymmetry. And then above that scale, they cancel and that's it. String theory never cancels it. It kind of over cancels it and then over cancels, over cancels it. So it goes always up and down. And there's no supersymmetry whatsoever. However, string theory does it in a very precise way, such that the bosons and the fermions cancel out. And there is the name asymptotic, which I didn't like too much. There is the name misaligned SUSY, which has some advantages, but some disadvantages. There is no SUSY. However, the bosons and fermions are oscillating. So one can think of it somewhat as some misalignment, but the states are growing. So while they oscillate, they also keep growing and growing. And one can make that very precise if you know a little bit conformal field theory. So the left-handed and the right-handed, left mover and right movers, they grow according to the central charge. So for the heterotic string, that would be 24. For the bosonic string on the left, I think, and the right movers would be the superstring, a central charge 12. So the states overall, they grow exponentially with the square root of n and this prefactor. And for the heterotic string example that I just mentioned, we can split them into net fermions or net negative state numbers, which have integer n, and then we have half integer n for net bosons. And actually both of them grow exactly in the same way, except that the net fermionic numbers have a negative n. So one can make this very precise in the partition function. If instead of I sum over integer and half integer, I split it up in a sum over integers and half integers, then I have two sums, one negative and one positive, and they both diverge like this exponential, but with opposite sign. And they do that in such a way that the net exponential growth is smaller than this. So there is a reduction in the exponential growth. So the leading order exponential diverges. And what Keith did in '95, he proved that using conformal field theory. So here's a plot of this exponential growth for bosons and fermions. It goes more or less through this because the corrections are subleading. So if these values are sufficiently large, you don't see the corrections, but the corrections are crucial, and I will get back to them in a little bit. So using conformal symmetry, Keith proved that the leading divergence always cancels in non-supersymmetric string theories. So that's very exciting, and it seems we are clearly on the right track. I mean, this oscillation has to mean something. However, there are many subtleties. So there is an infinite number of power law and exponential suppressed subleading corrections, which I will mention below. All of them need to cancel, otherwise you can show this doesn't work. So Keith said, okay, I know they all have to cancel, I conjecture they all cancel, but I don't know how. And this was one of these issues where we now made progress. I think we have a better understanding of how this cancellation works, and we can kind of prove how it works in this average sense. Now, the angle where I came from, so I was interested in KKLT, anti-branes on top of O-planes, and there we studied a lot of non-supersymmetric brane setups and open strings, and this is somehow also connected to misaligned supersymmetry. And there has been already a paper on open string misaligned supersymmetry, and it also requires a similar oscillation that was shown in this paper, 2000. Otherwise, there would be some instabilities, but I'm not aware of an explicit example. But it's not hard to come up. I'm sure everybody could come up with an example. So the example we came up with is an anti-D brane that would sit on top of an O plane. That would be one possibility that people discussed, uplifting ADS vacuum and KKLT. It's related to a nonlinear version of supersymmetry that I have been studying, but here I will not go into those details. I will just look at flat space, take any anti-brane and put it on top of an O plane, and the O plane projects out part of the spectrum. And what it actually leaves is, at the massless level, it leaves 8 fermions. So here the brane, these are kind of the Goldstinos for the broken supersymmetry. And at the first massive level, it has a net number of 128 bosons, and then it has fermions and bosons, and it oscillates. So this is the spectrum of an anti-D brane on top of an O plane that was calculated by many people, for example, Untitled Chapter and others. They calculate the partition function. I'm not sure what the original reference is, so we didn't certainly invent that. This has been calculated a long time. And you see, it exactly looks the same way. It oscillates. At the massless level, you have only fermions. First massive level string scale, you have only bosons actually here, and then only fermions, only bosons. So there is again the same kind of oscillation. And the question which we still want to hope to address in the long run is, this actually has some underlying nonlinear supersymmetry. I don't know whether that is related in any way to this misaligned SUSY, the oscillations. I have no idea. Naively, for the non-supersymmetric string, there should be no nonlinear version of supersymmetry. There should be no SUSY at all. But anti-branes, if you open Polchinski, they break supersymmetry spontaneously. So if it's spontaneously broken, you would expect that once you add in the whole spectrum, the whole tower of states, it should be somehow restored. Well, what we see in the spectrum here is this misaligned SUSY. So I'm not sure yet whether there's a connection and what all of this means. But let's now look at the cancellation beyond leading order. That was one of the caveats where Keith just knew it had to be there, but he couldn't prove it mathematically. Yeah, so in 1994, it wasn't quite clear, and it's essentially a little bit of math in the math literature that well, maybe, and also our simple example. So we got a very simple example, and you just stare at the example, and you ask, how does this happen? And then you kind of see it. So I will show you the picture. But the math where it's encoded is, so fittingly, it's a Ramanujan, Hadi Ramanujan Rademacher sum, and in particular reviewed in this paper. So many people have studied that, but if you have a partition function like for the closed string, or even for the open string, and you have a subgroup of the SL2Z. So for the closed string, we have the modular group SL2Z, and the partition function is invariant under that. That makes things a little bit easier. But most of these results carry over for subgroups of the modular group. So for the open string, while you don't have modular invariance of the partition function, and then people are a little bit more reluctant maybe to work on that, you still have a subgroup of SL2Z. and then the same results essentially apply, because the mathematicians extended that in many different ranges. So if you ask what are these AN that were oscillating bosons, fermions, bosons, fermions, you can actually write them as an infinite sum over some prefactor, which is kind of a phase. M depends on the particular function, whether I do open string, heterotic, and so on. And this whole thing is a Bessel function. So before we said these states grow exponentially. So this Bessel function essentially encodes this exponential growth here. There's a central charge, left movers and right movers for closed string, or just for the open string, there's just one central charge. Here's the exponential leading growth, and the Bessel function includes all polynomial sub corrections, but via the sum from k equals 1 to infinity, it includes an infinite number of exponentially suppressed terms that all need to cancel. And that was something that Keith couldn't show before, but I think now we have more or less an understanding how that happens. So to explain that, at leading order, one finds there is for k equals 1, a leading term for bosons and fermions. So in our example right now, we split it in even and odd ends, even for fermions, odd for bosons, but similar for the heterotic, it was integer n versus half integer n. So what Keith had proven mathematically rigorous without a doubt, if you split that into bosons and fermions, then you find these leading terms, where we now included also some polynomial subleading terms in these Bessel functions. And these cancel exactly because these two functions are real and they are the same. The issue here is you need to compare even and odd n, or you need to compare integer and non-integer n. And this works here because these are continuous real functions. But if these are not continuous real functions, then you're comparing pears and apples. So how can you say that something cancels? This only works for real functions, which is only the case for the leading k equals 1 contribution. Once you go to k equals 2 already, and then 3 and so on, you find these functions become complex. So if I try to compare this term, which is only defined in principle for odd n, with this term, which is only combined for even n, then I can't really compare them anymore because they become complex. And then what do? Do I take absolute values? Do I take real parts? There becomes a huge ambiguity. And that's why it became kind of impossible beyond leading order to cancel bosons and fermions. And it was very unclear, how would one do that? How does one properly set up this problem? And so here, this is kind of sketched. There is a leading contribution for bosons and fermions, and they exactly cancel. However, what we noticed when we looked very closely, the subleading corrections, they do oscillate around the bosons themselves, and similarly for the fermions. So subleading corrections do not cancel between bosons and fermions. If initially you counted your boson degeneracy, you found this, this, and this, and then you look at subleading corrections, they can actually tell you, oh, you undercounted, so I need a little bit extra. Here, I need a little bit extra. And here, you totally overcounted, so you need twice as much takeaway. So, and then these kind of oscillation around the original count, the leading exponential growth, they actually cancel. And here I plotted a slightly more complicated pattern where it's just not oscillating up and down, but you have 2 times overcounted, 1 times undercounted, 2 times undercounted, 1 times overcounted by twice as much. And they can average out. So what we find is that beyond leading order, these subleading corrections, they cancel within each sector. And that is possible because the leading order term sometimes overcounts and sometimes undercounts. So it's kind of boson cancel with boson, but it's just because the initial count was too naive and doesn't take the precise number. Okay, so this is slightly technical, but this is kind of the upshot that we found. So we can, for the experts, this is related to a particular property of the Kloosterman sum, which are these ANs. They are some phases that appear in this Hardy-Ramanujan Rademacher sums that work for these modular functions. So, oops, sorry. So using these properties, one can actually prove that the subleading corrections cancel as expected by keys and as required to get a finite answer for a cosmological constant or other things. So this is some property of this Hari-Ramanujan-Rademacher sums. This should extend to all other cases, but we have explicitly checked it for the SO16 heterotic string. And there it just works exactly in the same way. For left movers and right movers, the subleading corrections kind of cancel separately among themselves. And then in the full partition function, that also cancels then trivially. Okay, so this is not a total miracle. So I find it very cool how a non-supersymmetric string can give you finite answers. And it's actually even cooler, I will tell you in a second. But this doesn't solve the cosmological constant problem or something, right? For that, we have the landscape. So if you look at an anti-D brane on top of an O plane, you find at tree level from the dBi action, you just integrate over the walled volume minus square root g. So you find the string tension or the brane tension e to the minus phi times the volume. Now, if you calculate the one loop correction to that, which is essentially what I mentioned before, you can extract it from the partition function. One finds at one loop, there is a p-dependent prefactor, some number order 1. There's again the tension and the volume. And if you combine them, you find essentially you have the tree level term plus some order 1 number e to the phi. So you find the one loop correction that is suppressed by one loop by the string coupling and multiplied by some order 1. So there is no big surprise either way. If I asked you before what should be the cosmological constant, you would have said it's string scale. So the outcome is, of course, it is string scale. There are corrections that are suppressed by loops, and the coefficients are order 1. So everything comes out exactly as we expect. Miracle. The answer is what we expect, but it's interesting and fascinating to see that you can actually get finite answers because the bosons and the fermions cancel. And this particular cancellation, I think there is much more to this. So it's not just, okay, I get a finite answer, I get the string scale as everybody expected. No, I think there is actually more to it. And that I just wanted to flash on the last few slides. Yeah, so here, if you ask your QFT friend, he also would say, okay, string scale, of course, in string theory, the answer should be string scale. But there is more to it. There are particular interesting cancellations between the bosons and the fermions. And I initially mentioned this cosmological constant and the scalar masses. And if you talk to somebody who works on SUSY, they define super traces. And they say, okay, I write everything in terms of these super traces. The super traces are essentially just sum over states minus 1 to the f, and then the mass of each state times 2 to the beta. So beta equals 0 would kind of be just the sum over the states, which we had before as this leading order for the cosmological constant. If beta equals 1, then you just put in the mass squared there. And these super traces, they encode the corrections to scalar masses and to the cosmological constant. So we have been mostly discussing this, but there are further corrections and logarithmic divergence. So there are quadratic, and logarithmic divergent terms. And how do you calculate those in string theory, and what is the answer? And this was actually done here by Deans, Moshe, and Myers. They actually managed to show that in d dimensions, the super trace vanishes as long as 2 beta is smaller than d minus 2. And when beta is d minus 2, then the super trace is actually proportional to the one loop correction of the cosmological constant. So in particular, if you live in 4 dimensions, you find in non-supersymmetric string theories proven that have no tachyon, the super trace m to the 0 vanishes. And the trace m squared is actually proportional to the one loop correction of the cosmological constant. So if you somehow have small corrections, I will say it later again, to the cosmological constant, you would kind of solve the hierarchy problem. Because again, this was appearing in the divergence of the Higgs, and this was a log divergence. This was quadratic divergence, and this was a log divergence. you have to be slightly careful here about the states that couple to the Higgs versus all states. But in principle, you have this constraint. If you just do the calculation in flat space, d equals 10, put a brane on top of an anti-brane, we checked it, or the heterotic string, you have the first supertrace vanishes, the second supertrace, the third, and the fourth supertrace vanish. The fifth one is actually proportional to the cosmological constant. So these new non-supersymmetric string theories, they have no supersymmetry at all, but they have totally crazy properties. I mean, well, I don't know, at least for me, it seems, right? If you tell somebody you have a non-supersymmetric theory, why would all these supertraces vanish? So they have very peculiar properties, and they might be very interesting in terms of the hierarchy problem. So if you solve the cosmological constant problem somehow with the landscape, and you somehow manage to have small corrections, that might already help with the hierarchy problem. Yeah, so here's a kind of summary. Some supertraces vanish in all non-supersymmetric tachyonic-free theories. And in d dimensions, for example, the supertrace m squared, that would be the one loop divergent for the log divergence for the scalar masses, goes like the one loop corrections to the cosmological constant. So if that is very small or even zero, that could solve the hierarchy problem, or at least make it technically natural. So this is something I haven't worked on in depth, but there exist extensions by Stephen Abel and other people where they also look beyond one loop. So this extends to some degree beyond one loop. It just becomes harder. They also found cases where they managed to make the cosmological constant exponentially small. So in some cases, you can ensure zero cosmological constant at tree level, and then you can ask, can I maintain that at one loop, two loop, and so on. So if you just have, like we had a brane, anti-brane on top of an O-plane, at tree level it's large, and then the loop corrections are also large. But in heterotic, in some examples, well, in the SO16 times SO16, for example, the tree level is zero, and then you can ask, what is the one loop correction? Can I maintain that to be small, and so on. And that is ongoing work, and other work, yeah, I mean, there's work related to the hierarchy problem, I think from Stephen Abel and Keith Dean, which I heard a talk about, and it's forthcoming. Yeah, there was some paper by Alan Faraji, which I haven't looked at a few days ago, but I didn't have time to read it. There was some paper by Aaron Palti about fermions and the swampland, where he also discusses these non-supersymmetric string theories. And there, I think they provide a really nice playground to test all of these swampland conjectures in non-supersymmetric setups, and maybe that will help us get more support, or maybe modify the swampland conjectures depending on what the outcome is. Okay, so this brings me to the end of my talk. So there is this idea in string theory of misaligned supersymmetry. There is no supersymmetry. There is a cancellation, however, between fermions and bosons. However, the cancellation does not happen at any mass level. So at no level are bosons and fermions ever canceled. At no energy scale do they really cancel. You need to take into account the entire tower of states. You need to take into account this infinite spectrum of string theory to get actually this finite answer. You cannot truncate or anything like this. The cancellation happens via some intricate averaging over states. So at leading level, it's just essentially net bosonic versus net fermionic, but at subleading cancellations happen between bosons, for example, themselves, or fermions themselves in some cases. So we understand it a little bit better, but I think there is much more to be discovered. Yeah, so I mean, this might have implications certainly for the hierarchy problem, for the standard model. There might be an intriguing connection to nonlinear supersymmetry, which I hope to understand better, but I don't understand it yet. And there might be, of course, many more applications to string phenomenology and the swampland, and it might help us hopefully settle some of the questions that deal with non-supersymmetric string theories. Okay, so thank you very much, and I'm happy to answer many questions. if you have some.
Okay, so let's thank Timm for this wonderful talk. So yeah, we can take some questions.
I would have a question, if that's okay.
Yes. Yes.
Hi, Tim. So I'm not at all an expert, so my question could be far off here, okay? But the cancellations you were talking of are very stringy in the sense that you need an infinite tower, and then you have cancellations between subsequent sectors, right? Nonetheless, I remember that also in pure field theory, okay, there exists sometimes surprises like this. But don't ask me the references, but you might know them from the work of the Saclay group. When it comes to anti-D3 supersymmetry breaking, they have looked at the field theories, so the purely field theory perspective of the D-brane, well, field theory. And they also noticed, or they could use results about non-renormalization theorems for non-SUSY field theories. So I'm wondering to what extent could this be related to each other?
It could be. I mean, I'm probably not enough, I'm not that knowledgeable about pure field theory. I mean, I guess, of course, a field theorist could reach similar conclusions, right? You just tell them there's an infinite spectrum. I somehow want to get a finite answer. He will tell you there needs to be some oscillation, and then if you tell them the spectrum grows exponentially, I have no doubt that any field theorist can reach similar conclusions. It's just, for me, interesting to see that this particular setup is kind of realized in string theory, and it seems fairly universal for all non-supersymmetric string theories. That and I mean, Keyes explains this so well. I can't do it, but I mean, he says this is spectacular. We want to solve hierarchy problem. We want to solve cosmological constant. SUSY just can't do it. SUSY needs to be broken, and then so how do we get a symmetry that does not need to be broken, that is compatible with the standard model, that's compatible with our universe? What kind of symmetry can we come up with? And he said, well, string theory has conformal symmetry and relates the UV and the IR in a very particular way, and that guarantees this finiteness. And this is kind of what we see here in this particular oscillation and growing of the spectrum, I think, this underlying conformal symmetry on the worldsheet.
Great, thanks.
Yeah.
Any more questions?
Hi, can you hear me?
Yes.
Hi. Yeah, I also have a question, if that's fine.
Yes.
Yeah, wonderful talk, Tim. Thanks a lot. I just wanted to be sure to understand. So you managed to prove this this cancellation and this nice averaging in your example with anti-D3, right? Or with right? But
yes.
That's not the same thing as the bosonic, or as the SO16 times SO16 heterotic.
Yes, yes. Yeah, I flashed that too fast for you. So
because you write verified, so I was not sure what it meant.
Yeah, so essentially, if you want to calculate any degeneracy for these modular functions, there is a particular way of writing it as an infinite sum. And that works for any function. It could be the bosonic left movers and heterotic right movers, whatever. It could be the open string, whatever not. And the way we found cancellations is by properties of this AKN. So, so here's a cancellation which each sector results from properties of this AKN. And that is some universal property that doesn't really take into account, oh, I'm open string, I'm SO16 or whatever not. This is just a very universal feature of this. And yeah, I mean,
I see. I understand. So it goes beyond your example indeed then.
Yes, exactly. I would expect it applies to any example. There are some subtleties, which I have to say, which we are trying to figure out right now. In principle, this cancellation works and should work, but these are infinite sums, and then you need to move the limites left and right, and there should be a finite answer. So there must be, while moving these sums back and forth, there must be somehow a finite answer that remains that gives you a non-zero finite answer, which we haven't completely figured out yet. But in principle, we see how any subleading correction at any finite level cancels for any non-supersymmetric string set.
Thanks a lot.
More questions? Okay, if there are no more questions, let's thank Timm once again. So yes, so we can move to the final talk of the session. Thomas, can you share your screen?
Yep, let me try to share it. Then I have to share this screen. Wait, this one. Can you see it?
Yeah.
I think I have to do F5 to get it to full screen. No, I have to do view, full screen mode. Okay, I think I'm ready.
Okay, so welcome everybody to the final talk of the day by Thomas van Riet from Leuven, and he will be telling us about De Sitter, landscape, and Russell's teapot. Okay, so over to you, Thomas.
Okay, thank you very much. And I would also like to thank you and the organizers for the invitation. It's an honor to give a talk here. I realize this is the last talk of a long day. So my talk is rather sketchy and heuristic. I just try to connect various ideas. So also non-experts, I think, can sort of get the picture here. So the overarching topic is vacuum energy in effective field theory, but also from the swampland point of view. And of course, especially at the beginning, will be a little bit heuristic, and you can easily, hurt me there by asking questions. But nonetheless, I invite you to do so. Okay. So most of what I'm going to say is based on work in progress on seemingly orthogonal topics, but I really try to connect them here. And I also talk about two recent published works with Farakos and George Stringas. So what I really want to do for this talk, I want to connect two different viewpoints on, say, vacuum energy, field theory and string theory. One is from the point of view of effective field theory, and the other one is the swampland sort of string theory picture, okay? But I'm trying to argue that both pictures should be sort of consistent with each other, because there's of course nothing wrong with effective field theory, and at least some of the swampland things certainly make a lot of sense. Okay, so the topics I focus on are, on the one hand, the sign of the cosmological constant, so with positive or negative, and the size of it, okay? And when I discuss the size of the cosmological constant, I'm equally talking about negative cosmological constant, okay? And therefore, I have four sort of blocks here, and I will go through each of them. So I will discuss, say, the sign of the cosmological constant in effective field theory, its size, and I will discuss the same for the swampland string theory point of view. I will not be complete at all with references, so please let me know if you feel I missed something crucial, but I certainly did, because this is the point of this talk. Is not that it's an overview. I'm just trying to connect ideas in a very biased way, okay? So let me start with effective field theory, and what about, the sign or of the cosmological constant and whether it's constant, okay? So I think especially the problem of it being constant is non-trivial. So if the cosmological constant is negative, we can have supersymmetry. And then you could, of course, think that there is non-renormalization and say the cosmological constant is not really corrected in case it's enough, if there's enough supersymmetry. But now I want to focus sort of on the Sitter space, so on a positive cosmological constant. And you should ask yourself the question, why should it not undergo some RG flow? Okay. And if a cosmological constant undergoes an RG flow, what does it really mean? Because it's a little bit less easy to understand if you compare RG flows for, say, a dimension 4 operator with respect to a mass term or something, okay? But I would say if a cosmological constant runs, the Sitter isometries are certainly broken, and it will become more and more visible at certain scales. And the question is, oh, could we detect it eventually? Okay, that's I think, an interesting question. And what is the physical mechanism behind a possible running of the cosmological constant? I would say it should be something probably similar to the Schwinger's decay of electric field, or to some charge screening in QED. All right. So what do we have in the Sitter space, which makes it special, is that, you know, there's, if I take a particle-antiparticle pair, which I produce out of the vacuum, of course, they gravitationally attract each other, but a positive cosmos constant is also, it also means that on large scales, they gravitationally repel each other. So there you can actually create spontaneously particles out of the vacuum if the cosmos constant is negative. This is very well known. And this is the reason that the Sitter space has a certain temperature proportional to the Hubble Hubble constant, sorry, okay? Another question is, okay, if I, similar, you know, to the decay of an electric field that I sustain between two conducting plates, is similarly the Sitter space decaying because of the backreaction of the created radiation. So what would be the very heuristic picture to keep in mind is that it's kind of similar to a black hole, but this time you're inside the black hole, okay? So here I depict the Sitter space, here is my cosmic horizon, I get particle creation, and super heuristically I can say, okay, then the particle with negative energy is leaving the horizon, the one with positive energy is being detected by me, and this backreacts on the Sitter space, and it makes, say, the Sitter radius grow, which means that the cosmos constant would go down. So is this true? You know, is the Sitter space cooling down? Is it undergoing an energy flow? And this seems to depend, if you check the literature, which is, by the way, highly confusing and complicated, but if you check literature, it could be that this depends on the choice of vacuum in the Sitter space. But as you probably know, I'm trying to go to the next slide, there we have it. The vacuum in the Sitter space is not uniquely defined because we don't have a time-like Killing vector, which is global, okay? So, of course, there is some room, and a famous set of vacua are called the alpha vacua. And the way you can think of the alpha vacua, this is a formula I copy-pasted from Ottola's famous paper from '84. You can think of it, well, there's just a standard sort of Bogoliubov mixing, as we have for black holes, and the coefficients which mix my raising and lowering operators, which act on my vacuum, they have to obey the following condition, okay? So this sort of gives a one-dimensional complex dimension freedom in your vacua, and they're called the alpha vacua, all right? And the most famous vacuum is the one where this coefficient beta equals 0, and this is sometimes called the Bunch-Davies vacuum, or it has many names. Let me call it a Euclidean vacuum, okay? And so the point of view of the Euclidean vacuum is that in the Euclidean vacuum, there's probably no backreaction, okay? And the Sitter space is sort of sustained. The isometries are not broken, but when, imagine somebody could argue, in fact, no, the correct vacuum has a non-zero coefficient beta. If you check the literature, also there is some confusion. How would that backreact on the Sitter space? How would it lower the Sitter radius? And okay, what at least is always the case is that it would say go like beta. Sometimes there's even a power here. And then there's certain powers consistent with dimensional analysis, okay? And even there, so this is not entirely understood. Okay, so there are two things which are not entirely understood. What should be the correct vacuum? If it's non-Bunch-Davies, if it's not Euclidean vacuum, how is the Sitter space decaying, all right? Note that this is pure effective field theory. There's no string theory here, all right? Sorry, this is the wrong one. Now we go to the next one. So whether, imagine this is correct, whether this should be detectable really depends on the size of beta, the non-Bunch-Davies coefficient, but also on the particular power that should appear here. Now, if you check the literature on say, quantum field theory in the Sitter space, I can say it's genuinely difficult. But interesting, there has been lots of things happening in the last 2 years, but the things that have happened have all to do with certain worries about interacting fields in the Sitter space, okay? I'm thinking about old worries from Woodard and from other people. And I think many of these seem to be solved, but I'm not an expert, but they seem to have been solved. But what I want to do today is I would just want to stick to 3 fields, okay? So only free fields, no loops for the fields that are, non-trivial, etc. And the only thing that enforces decay would be the coupling to gravity. So what I'm saying requires really a finite Planck mass, okay? So we can check the literature about what are, the possible non-Bunch-Davies coefficients. And Mottola argued for an interesting one, which only applies to fields with a mass above the Hubble scale. He said, well, he has an argument on why these coefficients should be the Boltzmann factor, roughly speaking, okay? Another series of papers by my collaborator Ulf Danielsson, he argued that beta should be rather proportional to h, and there should also be the cutoff scale appearing so that you get some dimensionless number. And when you do this one, interestingly, you exactly get a saturation of the following inequality in case you would translate it into in the running of the CC in terms of some classical field rolling down a potential. Okay, you get exactly this thing which is called the de Sitter swampland conjecture, and the value of C that you get, which has been heavily debated in this inequality. So if C is order 1, this should have really measurable effects, and we should really, if you look at dark energy now, we should really see that its deviation from an equation of state parameter which equals -1 should be quite large, okay? Instead, with this quantum calculation of Danielsson, it is related to lambda divided by MP, Planck mass, where lambda is the cutoff scale, okay, which could be the string scale or something else. So this number potentially can actually be very small, and then the deviations from de Sitter space or de Sitter isometries are actually not so large. But the question is, really, you can probably discuss till infinity what is the correct vacuum, right? And my guess, based only a guess, is that probably or all or some vacuum choices are consistent, but is consistent the same as physical? That, I think, that is a crucial issue. And if you think about the same discussion for black holes, well, you can do the following for a black hole. Instead of taking the Unruh vacuum, which makes a black hole decay, we can use the Hartle-Hawking vacuum around the black hole horizon. And what is a Hartle-Hawking vacuum? You can think of it as somebody putting meters there, or some little demon that is just kicking back the Hawking quanta that which are sent to infinity. It sends it back inward. Okay. So in a Hartle-Hawking vacuum, a black hole is actually stable and it's not decaying in time. All right. So you could ask yourself, if we really insist on saying that string theory should be consistent with the Sitter space, then in this kind of effective field theory reasoning, you should hope that string theory picks the Euclidean vacuum, the analog of the Hartle-Hawking vacuum for a black hole. Okay, you should ask yourself, does that make sense? Okay, now imagine the following thought experiment. Imagine an alien society which has, discovered black holes. They discovered string theory, but for some bizarre reason, they didn't think of Hawking radiation, okay? And imagine they're very powerful and they do string theory calculations and they're trying to look for microscopic descriptions of Hawking radiation, of Schwarzschild black holes, okay? So they really want to construct the microstates. And what they assume for their microstates is that they also obey that they have a time-like killing vector, okay? Because they think that a Schwarzschild black hole is stable in time. Well, I think they should fail, right? Because in the end, if you have a microscopic description of Schwarzschild black holes, which we don't have at the moment in string theory, we should be able to see the Hawking radiation as well, okay? So the quantum geometry, of course, doesn't have a time-like killing vector. It's broken by it's broken by quantum effects. And you could wonder, are we sort of like these aliens when it comes to the Sitter space? Okay, because the Sitter space from string theory, I'm not saying we have shown it's impossible, but it seems so hard. Who knows? The reason is something like this. String theory is trying to tell us something, okay? Another related thing that you might have seen in the literature on quantum cosmology, not string theory, so more in the context of, effective field theory techniques, is this debate about Hartle-Hawking wave function versus the tunneling wave function of Vilenkin. Okay, maybe you have seen this debate, and you can ask yourself, is this maybe not the same debate? Because, there's also this debate on what is the right vacuum in the canonical QFT formalism. Okay, and whether this debate is rather about a path integral formalism. And the only thing I can say, I'm not a big expert, but in an upcoming work, we just have a side remark it has the following observation. What if I do the simplest thing, okay? I study the wave function approach, and I do the thing that everybody does to make life simple. I study it in mini superspace, okay? And then I'm essentially just solving, a standard, almost standard quantum mechanics problem. What we've noticed, I'm sure others must have noticed this as well, is that the difference between Hartle-Hawking and Vilenkin really depends, of course, as should be, on the boundary conditions you put on your wave function near A equals 0, where A is a scale factor, so near the Big Bang phase, okay? But which boundary conditions to take really depends on what is called your effective superpotential there, all right? And if you check what is your effective superpotential, especially near A equals 0, we cannot use classical GR. But imagine you take classical GR and you add, say, derivative corrections. It really depends on the detail of the sum over derivative corrections, whether your superpotential, for instance, it can easily go to plus infinity, which means that there's an effective repulsion. The universe, the dynamics doesn't allow you to reach 0 scale factor. And imagine this is how the UV completion works of gravity, say string theory, okay? Then you can actually see from these simple calculations that you actually need to pick the Hartle-Hawking wave function, okay? So the only thing I'm observing is that maybe this discussion, actually string theory should be able to shed light on it, okay? But I don't have the answer. I'm just mentioning how I think it could work. So let me contrast this with the discussions that we have had in string theory, especially in the context of the swampland, okay? So for that, let me remind you how we actually go about and construct vacua of string theory. So that what we can do is very, very limited. The only thing we can do at this point in time is construct vacua, which I call at the boundary of string moduli space. What does that mean? We can only do calculations when we are doing perturbative string theory. So that the loop expansion should be really under control, and we want to keep the first terms. And it's the same for the gradient expansion in the 10-dimensional supergravity picture, okay? So this means that curvature should be small enough and volumes should be large enough, right? So the two things that I'm trying to control are GS and say volumes, and both of them are as well fields in 4 dimensions, okay? So depending on how I stabilize them, my model is under control and I can trust it or I cannot. Interestingly, these quantities also determine the Planck scale through this famous relation, okay? What is quite striking of string theory, imagine I can put myself near the boundary of string moduli space. If I do a computation, what I get, and this leads to often confusion when I discuss with colleagues, what I get is something that's essentially almost a correct vacuum energy, okay? So that is a nice virtue of string theory. We can actually compute vacuum energies in certain corners of the theory. So that means that we can get the quantum information, which is kind of a dream for a field theorist, right? How can I really sum the whole tower of corrections and have it under control? So that is why it's interesting to do these exercises in string theory. And so you can ask yourself, okay, what did you find? Did we succeed? Well, as you know, it's a really tough debate. It's very complicated. And I can advise 2 complementary reviews, one of which is mine with my collaborator Danielson, okay? And what I want to do for this talk, there's so much, I just want to focus on 2 things. One is the history of KKLT, which I want to say something very quickly about, and then attempts for looking for classical de Sitter vacua. And actually in this conference, you will hear other talks about these topics, okay? So I will only be super brief. So let me start with KKLT. So to remind you, KKLT achieves full moduli stabilization in a supersymmetric ADS vacuum. And that SUSY ADS vacuum comes from quantum corrections to a no-scale non-SUSY Minkowski vacuum. So this is a bizarre case where we have some non-SUSY vacuum at 3 level, we add quantum corrections and we get a supersymmetric vacuum, okay? That's what KKLT did, which is quite amazing and nice. And then what they did, the second step is they uplift to metastable de Sitter vacua via this anti-D3 supersymmetry breaking. What is crucial for that to work is that you need to have a large warp throat so that these SUSY breaking effects can really be redshifted to small energy scales, okay? And of course, all of these things have been debated since the very invention of KKLT, okay? So I think since day one, people have not been agreeing with it. They had some criticism, this criticism was refuted, and this has been going on, okay? And also my own, some of my own criticism was refuted also by myself. So I'm just saying, KKLT sometimes feels like, the story of zombie resurrection. It keeps on, waking up, so to speak. Okay, keeps on surviving. So what about the last things that happened? Well, I think already this year we have seen quite some amazing things, which I think some of it will be on this conference. So I think, for instance, September, last month on the archive, I think it started very good for KKLT with these two papers. We did something crucial. Namely, they were able to show that the way you balance classical and quantum effects, you can actually do it consistently, because you can actually achieve, if you like, this fine-tuning between classical and quantum effects. But especially when it comes to the uplifting, so the issue of having large enough warp throats, that I think there was a later paper near the end of September, which so far I can tell is really a big issue that we should address, because it seems to me the end of the uplifting scenario, if it's entirely correct, okay? And the only way out at this point seems to be the large volume scenario, which is a bit more complicated. Okay, let me go to the second class of possibilities to construct de Sitter vacua in string theory, which I've worked on. And these are classical de Sitter vacua. And what do we mean by classical? In this context, we mean classical from the 10D point of view. So it means we can do supergravity, and on top of supergravity, we have orientifold and D-brane sources, okay? And this has mostly been tried in type 2A string theory. And the reason is that type 2A achieves something quite nice, at least for anti-de Sitter vacua, as was being shown by de Wolf et al. In 2005. They've shown that unlike KKLT, you don't need to balance quantum and classical effects. You can just, from classical fluxes and orientifolds, you can achieve supersymmetric ADS vacua, which are much less stabilized and which have a scale separation between the ADS scale and the Kaluza-Klein scale. And at the same time, these solutions are arbitrarily weakly curved and coupled. So it's quite amazing, okay? So you can wonder, within this class of solutions, can we also get de Sitter solutions, or within this class of models, can we also get de Sitter solutions? And what we already know is that for that to be possible, you need to sacrifice the Calabi-Yau geometry for some generalized Calabi-Yau geometry, which has to have negative curvature. And I think some of these original ideas have been developed in these two nice papers here. And then a lot of extra work has happened, partially by me and many collaborators and many other people, okay? But what is the problem? I think all attempts we've seen give problems. They give either small cycles, they give large coupling, they give tachyons, and typically combinations of all of these things together, all right? And I refer to talk by David on this conference if you want to know more about this. Sometimes it's claimed that the only thing you need to add in order to get rid of these problems are non-geometric fluxes. I would say this is highly unclear. Especially, I expect an upcoming paper by Eric Plaushin, who has shown in the models that have been tried that actually, if you look into the details, these papers have problems with the tadpoles, that they actually are not satisfied in a physical way, okay? And even if somebody maybe one day has a model, with non-geometric fluxes that still has a good tadpole, good solution to the tadpole condition, it's very unclear whether we would trust effective field theories with non-geometric fluxes, I would say, okay? So the situation is rather grim. And I would say there's enough reason to maybe hunt for classical de Sitter vacua in other dimensions. I know we live in 4 dimensions, but just for the sake of trying to find de Sitter vacua, which are simple, so we can stop having conspiracy theories against them, we can look for them in other dimensions. So you can think of dimensions higher than 4 and lower than 4. So when it comes to higher than 4, the only thing I know that is there is a proposal by Cordova de Luca and Tomasiello, which I think is very interesting, but it's unclear whether the solution is really there for 2 reasons. First of all, I was quite convinced by this paper by Kribiori and Junghans that the singularities that are in the solutions might not be physical, although this is not a clear-cut proof, but it's something that I think we should all look into it. And secondly, very recently, last week, the Saclay group had a paper showing that maybe these vacua are actually unstable. Okay. So let's go to dimensions smaller than 4. There was one study, there's not much, actually, I know of one study before by the Stanford group. And what I want to quickly mention today is papers I've been writing with these 2 nice gentlemen. Okay, and so what did we do? The first thing we did is to show, similarly to what de Wolf et al. Did in 4 dimensions, we showed that there exists classical moduli stabilization in supersymmetric ADS vacua. So this is not the sitter, this is ADS. At arbitrarily weak coupling, arbitrarily weak curvature, and with arbitrarily large scale separation, okay? So this is kind of nice. And then you can wonder, okay, so the only ingredient here, instead of a Calabi-Yau, because you're going to 3 dimensions, you'd actually need an orientifold of a G2 space, okay? So similar here, you could say, well, if we can get all these nice things for SUSY ADS at the classical level, can we somehow break SUSY and get the sitter space? And what we have shown is that it seems to be possible if you allow anti-D2 and anti-D6 sources. And what's even nicer is that we don't have to sacrifice the G2 holonomy. At least in the smeared limit, we don't have to. And this is quite unique to 3D. Okay, this is why 3D is pretty nice to work on. And our model is in a way simple. But if you see this picture, you might not get too happy. So this picture shows that there are 7 intersecting O6 planes, which was also already needed for getting the ADS vacua. And the way they intersect is dictated by the calibration condition. And on top of that, we just needed F0 flux, so Romans mass, F4 and H3 fluxes. And to break supersymmetry, we added the anti-D2 and the anti-D6 planes, okay? And I think the most amazing thing we achieved, I was really surprised, I couldn't believe it, is that we were able to evade the usual tachyons that tend to be always there, okay? Then when it comes to small string coupling and large volume, I think it's only marginally okay. I quote the numbers here, okay? So it depends on whether you're happy with this or not. I feel that in the string pheno community, people would already be kind of okay with these numbers. But here, you know, I think you should mute the trumpets for a very simple reason, which I found also quite interesting. What we have shown is that exactly the region where our closed string tachyons, which are almost always there in this classical de Sitter vacua, exactly the region of our parameter space where we could get them to vanish, okay, is the reason where new open string instabilities appear. And these open string instabilities or modes are typically ignored. We didn't ignore them. And the only thing you need to know is this picture, okay? So what is this? These are like some flux quanta related to the supersymmetry breaking, and this is some other flux parameter. You don't need to know the details, but you just need to understand this graph. The solutions lie on a blue curve. And of course, you need to quantize them, so that this is why I dotted it, okay? And the instabilities in the closed string sector appear to the right side of the red line, okay? So what you do is you say, okay, I follow my curve and I tune the numbers such that I go inwards, but what happens then? The open string instabilities, which are typically ignored, they lie above the green line. So amazingly, this curve exactly turns to that region, okay? And to me, this is a typical example of a sort of de Sitter conspiracy that, you know, it kind of always fails, right? So the Sitter model building, you should really compare it with this game of whack-a-mole, which I think you know, you need to whack-a-mole and then it just, another mole rises somewhere else, right? So this is quite, in a way, annoying, but I think, no, string theory is maybe trying to tell us something very deeply, okay? Now, let me move away for a moment from the Sitter space. Let me just discuss, okay, what about the size of vacuum energy, okay? And let me go to EFT and then let me go to the swampland and then my talk is done. Okay, so what do we know in effective field theory? Let me recap the CC problem in a very simple way. If I have a single massive field, a free field, and if I look at my loop corrections, then we essentially see they sort of scale like this if you use DIMREG. But the bottom line is very simple. The picture to keep in mind is the following. If you tune if you tune the bare CC such that the sum between the quantum corrections and the bare CC is close to 0, then really any tiny change in the ultraviolet, something you don't control, would completely alter your result, right? So here is a typical picture. If you move from the ultraviolet to the infrared with a relevant operator, you just, you need a fine tuning if you want to get it small in the infrared, okay? This is something we all know very well. So let me contrast this with, how we compute these things in quantum gravity. And I already mentioned how we do it. We go to the boundary of moduli space, right? And there we have sort of a semi-classical description of space-time in a 10-dimensional way. And what is crucial, which I don't think is sufficiently highlighted when it comes to the cosmological constant problem, in string theory, at least in critical string theory, my metric splits into two parts. I have a metric on my compact space, which has a finite size, and non-compact space, the curvature thereof should give me the 4-dimensional cosmological constant. Okay. So this means that in string theory, I always end up with two length scales. I have the KK scale, which is the volume associated or the length scale associated to this blob. And there is a Hubble scale, which is a length scale associated to this thing, right? But if I construct solutions in string theory, and I need to check whether my vacuum can sort of be interpreted as 4D, what I need to check is that my Hubble scale is parametrically larger than my Kaluza-Klein scale. Or in mass scales, it means that the Kaluza-Klein mass should be way bigger than the mass scale of the cosmological constant, okay? And the collection of vacua that obeys this is what we call the landscape. So front-Rubin vacua, we do not call the landscape, right? The landscape, in particular, applies to vacua with this bizarre property, okay? Okay, that's the string theory side, but what happened to the quantum field theory lore, right? So in quantum field theory, we say, well, you know, any tiny change, it would completely change my cosmological constant, and that is true. Imagine I construct some vacuum, say KKLT, and I want to get the standard model. What do I need to do? I need to add sort of extra brains in order to get, you know, gauge groups, etc. But then, of course, as you know, if you do moduli stabilization, the moment you add stuff, you need to do everything again. And so your vacuum will be sort of a little bit corrected. And this computation in string theory is sort of almost classical, so to speak. You again minimize the new potential. But of course, and that is because these brains backreact on space-time. Whereas in quantum field theory, this would be a non-trivial calculation in terms of loop diagrams. Okay, so what about the naturalness? Because that's a real issue at stake in quantum field theory. Well, the effective field theory expectation is that the typical CC is of order 1 in fundamental units. But I can take to be my fundamental scale to be called Kaluza-Klein scale. But you see, here is a problem. This is what naturalness says. And actually, those of you that construct flux vacua, you actually know that this is typically what happens. Just, you know, take ADS5 cross S5. ADS5 is as big as the S5, right? So this sort of expectation in quantum field theory that a natural CC is, you know, order 1, it's indeed true for simple flux vacua. But what I think should be emphasized is that this would also mean that solution doesn't look 4-dimensional, right? And this I really underlined. What I'm trying to say is that the failure of a solution to look 4-dimensional is the same as not having a CC hierarchy, right? So 4D QFT makes the false prediction clearly if you look at the sky of a large cosmological constant. But again, you can only use 4D QFT when you have scale separation. And this is something which you could think of as a circular reasoning. We have to be really careful when we use 4D QFT arguments in string theory, because in order to use them, you have to already put in that we have a separation of scales, okay? I think this is not sufficiently emphasized. Okay, so what I try to argue here, what you really need to understand in string theory is how the hell can you have this amazing hierarchy between the two length scales in my 10-dimensional metric, okay? And this is the same question as why really does the universe look 4-dimensional to an observer, right? And how would a landscape person go about to answer the question, why do we live in 4D? Well, such a person would say, vacua of all kinds of dimensions exist, and we just live in 4D, by chance and by entropic reasoning. Let me for a moment assume a landscape. Like that landscape person, what I'm trying to tell you in the next slide, and I'm almost done with my talk, is that even if you buy the landscape philosophy, there can still be a dynamical reason why there is 4D, okay? Which really says something about the CC problem, okay? So assume for the moment a landscape of vacua of all possible dimensions, right? So there will be vacua with 2 large dimensions, with 3 large dimensions, 4, etc. Okay. And then you, of course, once you allow that, you have to realize that you can tunnel between these vacua, right? So what I'm going to do is I'm going to pick those string theory vacua which have no hierarchy problem. And what are these? Well, by definition, these are vacua which are 1-dimensional. These are vacua where you just have time, and all spatial dimensions are equally large. So M10, my 10-dimensional manifold is M1 times some 9-dimensional space. Okay, you can construct this vacua, and I think everybody will be convinced it's a simple counting argument that they would completely outnumber the 4-dimensional vacua, right? Because there are way more 9-dimensional geometries, there are way more ways to put fluxes, branes, etc. Right? The only catch here is that 1D vacua are not real vacua, because energy in 1 dimension always has to be equal to 0. And I will come back to that, what that means, okay? But it's not so crucial. Well, the subtlety will come back later on my next slide, and then I'm almost there. So I said, can we tunnel between these various dimensions? Yes, you already know an example in KKLT. Here I put potential again. This field is a volume modulus. In KKLT, one of the decay mechanisms is to tunnel out. If you tunnel out here, you tunnel from 4 dimensions to 10 dimensions. So tunneling between dimensions is nothing weird. We are very used to it, okay? So what we have done in a non-stringy calculation, just something in effective field theory, in an upcoming paper here, is what we have done. We say, okay, let's assume we are in a 4D vacuum. Can we, from that 4D vacuum, can we construct 1D vacuum, right? Just as and maybe can we then tunnel from this 1D vacua back into 4D? Just to sort of make that stringy picture of my previous slide to materialize it, okay? So what did we do? We took like Einstein Hilbert with a cosmological constant in 4 dimensions together with an axion term, okay? There's an axion. And I use this axion to put 3-form flux over the spatial dimensions. If you then analyze your 1D model, you get something like this, okay? And so this is my potential, and the fact that my potential goes up here, okay, is actually coming from alpha prime corrections, okay? It comes from higher derivative corrections, and X here is a scale factor, so when it becomes small, we expect these things. And so the only thing we have done in our model, okay, so this is all computed, this stuff with this Lagrangian, and we say, what if the quantum corrections are such that my effective potential goes up, okay? This we cannot prove, but it either goes down or it either goes up, and we say, okay, let's assume it goes up, okay? Then there's a pocket here for the universe, you see? Here is a pocket, we could be trapped here. What would this kind of 1-dimensional universe be? Well, energy is always 0 in 1 dimension, so it's a universe that bounces back and forward, okay? It's sort of breathing. The 3 dimensions are breathing, but they're super tiny, and at some point they tunnel out, okay? And when you tunnel out, that's when you decay to the 4-dimensional universe. Now, what we notice and what I mentioned before, when you really have this behavior, the natural wave function solution is the Hartle-Hawking state. And that would mean that the way I tunnel to large 4 dimensions really has a Hartle-Hawking weighting. And then my probability to tunnel to a vacuum with a cosmological constant lambda is given by this number. So you see, to tunnel, so what I've done here, and this is essential, okay, what is the bottom line of what I'm trying to tell you, all right, is that I can start, if I sort of believe in a landscape philosophy, I can start with a completely natural vacuum. And I'm claiming they are manifestly dominant of the unnatural vacua, because these are just what I call the, you know, the vacua in 1 dimension. They should dominate. There are way more of them than 4-dimensional vacua. And I'm trying to argue is that you can easily tunnel to other dimensions. And if I just took, for instance, the tunneling to 4 dimensions, they would sort of be favored, small cc would be favored by the Hartle-Hawking weighting. So I go from a natural to a completely unnatural situation. You can also ask, okay, of course, with your model, you can certainly tunnel to 2 dimensions, 3 dimensions, and so on, and I agree. But at least if you ask me, can you tunnel to 5 and 6? I don't know, because unless somebody here knows, there is not a single suggestion for how to obtain scale-separated vacua in dimensions higher than 4 in string theory. So anyways, in string theory, 4 dimensions is for sure something special. Okay, I have 2 more slides. This is my last part when it comes to the swampland. So here I discussed, you know, the size of a cosmological constant from the point of view of effective field theory viewpoints, which are addressed a little bit with, you know, landscape ideas, etc. Here I purely go to the swampland philosophy, okay? And these are 2 more slides. So what does the swampland tell us about the size of vacuum energy? Let me stick really to anti-de Sitter space because that is most well established, all right? And what I've said before is that, okay, there are examples in string theory where we claim to have a separation of scales between the Kaluza-Klein scale and the ADS scale. And that separation of scales means small vacuum energy. That is what I try to argue. And this famous solution is by de Wulf et al. In type 2a. And here I put the numbers. So there is some number n, which is the F4 flux quantum, which is unconstrained by tadpole. I can take it to infinity, and I will take it to infinity. The volume scales like this. String scale, the string coupling scales like this. It goes to 0. Volume becomes very large, but the ADS length grows large faster. So the ratio goes to 0. Okay, that was the amazing result of de Wulf et al. So this means that it is possible to get small vacuum energies. However, people have been worried about this paper, in particular because of the back reaction of the intersecting O6 plates. Okay, and people have been saying we should worry about them. Personally, I argued in a recent paper one should not worry about them in a large volume and weak coupling limit. But the solution is, is still contrived, especially because of the arguments by Banks et al. And Sethi et al. But I would say when it comes to actually constructing the back reaction in detail, there has been some recent interesting progress by Junghans and Marchesano et al. And what they've done is they've constructed the back reaction of the orientifolds at first order in some perturbation series, okay? So this is not a full result, we don't know yet, but it's already looking good, I would say, personally. However, this result clashes directly with a scale separation conjecture in the swampland by Lust, Palti, and Vafa. And their conjecture was, that this quantum field theory expectation that this is order 1 is always correct, okay? However, within the same logic of the swampland, I think this is a beautiful paper by the Madrid group. They have shown that it's nonetheless, there is a clear swampland reasoning, which nonetheless makes it consistent. And what is crucial is that they can decouple this. So they adjust this conjecture of Lust, Palti, and Vafa in the following way. So Lust, Palti, and Vafa said MKK goes like lambda to the 1/2, but what the Madrid group did said, wait, if there are discrete symmetries, a ZK symmetry, then K should enter here. And there was a clear reasoning for this. And then they verified it explicitly. And when K can be taken to be large, you can actually decouple the two scales, okay? And that really seems to be the case with this paper. So what is quite amazing about the Madrid paper is they first argue purely conceptual with black hole thought experiments, and then they check it in detail and it happens to be correct, okay? So I think the swampland is consistent with scale separation. Actually, some people say, but you always need Romans mass, okay? I don't think that is the case, and this was actually already pointed out by other people. But the only thing you need to do is, if you want to get rid of Romans mass, is you need to sacrifice the Calabi-Yau geometry for some generalized Calabi-Yau geometry. And one example is a double T duality of the de Wulf et al. Solution. And then you go from a toroidal orbifold to some orbifolded nil manifold. So it is possible to get without Romans mass. And one of the projects I'm doing is say, well, if that is the case, we can lift this to M theory, right? And we can maybe settle the debate about the back correction of these orientifold solutions, because without Romans mass, type 2A solutions can always lift to M theory. And what is surprising here, and this is our main interest, is that in M theory, without sources, because as you know, orientifolds lift to local Atiyah-Hitchin manifolds, the M theory solution should be smooth. There should not be an explicit source. But this is difficult to remedy with an earlier sort of no-go by myself and my collaborators, which says that if you do an 11D compactification without sources, you always have ADS, that is okay. But you also always have a positive curvature of the internal manifold, and you cannot decouple the curvature scales. If you cannot decouple the curvature scales, can you decouple the KK scale? And that is very unclear. There's actually not a single example known for a positively curved space, okay? So there seems to be a clash with this. So either this points to an issue that, like Banks already pointed out and Sethi, there's something deeply wrong with these scale separated vacua, or, and this is what I truly am thinking now, which I think is super exciting, we can actually do string phenomenology in a different way. We don't need to have oriented folds and branes. We can maybe achieve full moduli stabilization already with pure geometry with fluxes. Okay, so the lift of the solution that we're looking at should be some generalized G2 structure, and it should give full scale separation and moduli stabilization, which is quite a striking thing. Okay, so in that sense, there would be nothing wrong with scale separation. And here is the last slide of my talk. That is in fact the second ADS conjecture, which is by myself and my two collaborators. And what is this scale separation conjecture saying? It's saying the following. Let me take the mass of the lightest scalar in an ADS vacuum, and here is the ADS length. Then we're saying that this can never be true, okay? So this mass can never be tunably large in ADS units. So what is the difference with the scale separation conjecture on the previous slides by Lust and Balti? They were saying this essentially for a whole tower. We're just saying this for a single light field. So what we're saying is that every ADS compactification from string theory should have always one field at least that is sort of light, but it doesn't need to be a KK mode, okay? That is crucial. Anyways, if this could be possible, the dual CFT would be a dead-end CFT without relevant deformations for which the lowest lying relevant operator has a huge mass gap, okay? So that is something which, by the way, has not been observed in conformal field theories anyways. From where does this conjecture come? What we wanted to do is we wanted to sort of make the de Sitter conjecture, which is very difficult to argue for precisely. We wanted to make it more precise, okay? And we said, imagine we can turn it into a conjecture about SUSY ADS spaces. This we can settle for sure in a few years because supersymmetric ADS is something we can calculate, okay? So what is the thought experiment here? Imagine you can violate our conjecture and somebody can make an anti-de Sitter space where this is huge. This means that if I look at the potential, I can make this a potential approach 0 from below and at the same time squeeze it so that it's super narrow, right? In such a potential, if I break supersymmetry, of course, I'm not gonna fall out, okay? So I'm gonna get a metastable de Sitter vacuum if I can break supersymmetry, right? Why? I'm very close to 0, so any SUSY breaking gives me positive energy. And because it's very narrow, I might not tumble out, okay? And the only thing it requires is that my SUSY breaking is small enough, right? So this is why we want to translate the speculative de Sitter conjecture into a less speculative ADS conjecture. And what we're saying is that you cannot have tunably large MR together with small enough SUSY breaking, okay? Interestingly, the small enough SUSY breaking is now exactly what people are debating is indeed impossible. Okay, so it's nicely consistent. And there are other arguments why a large MR is indeed kind of strange to have, aside from a CFT argument, which is not, you know, fully settled. But let me leave the details aside. Okay, let me go to the conclusions. What I try to argue is that a de Sitter landscape means I have scale separated vacua with exactly constant positive lambda. And I think that is highly non-trivial, both from the string theory point of view and the effective field theory point of view. So the question I leave to you is if we want to make the analogy between Russell's teapot, should the analogy be that the teapot is the de Sitter landscape conjecture or the no de Sitter landscape or the swampland conjecture? This is what I believe, but you can have your own conclusion. Thank you very much.
Okay, so let's thank Thomas for this nice talk. So we can take some questions.
Hi, Thomas. If I may, I have a few questions.
Sure.
You can hear me, right?
Yeah.
Great. Yeah, thanks for a very nice talk and many open ends and many ideas. That's great. I have two questions. I have a very naive one regarding almost the last slide. This conjectures about scale separation. I mean, do you have anything to say about states which would have a negative m square, but still above the BF bounds? Because in all this discussion, it's always positive m square in a sense, right? I mean, or at least in
no, sure. Yeah, sure. So,
of something with a negative m squared but above BF bound.
No. So exactly. So what we're saying, okay, is that like the typical holographic vacua have a negative m squared above the BF bound, right? Because you know it's difficult to find a field theory or CFT without a single relevant operator. Okay.
Exactly. Yeah.
So yeah, the only thing that we're nice to say is that, okay, it is possible to have some field CFT which is a dead end of an RG flow, so it doesn't have a single relevant operator, but then the lowest lying relevant operator should not be of a tunably high dimension. Okay, so for sure I'm totally fine, and I expect this, that a typical ADS vacuum tends to have tachyons above the BF bound, right? And then, of course, they're not useful for de Sitter uplifting, right? So this is why, for instance, KKLT is kind of nice, because the ADS vacuum they start with doesn't have that tachyon, right? Yeah.
So when you talk of lighter states, you don't mean those. You really mean...
No. Saying we have at least light states. Maybe there are tachyons above the BF bound, and
okay.
Slightly above. Yeah.
Okay. And sorry, second short question. Since you mentioned this idea of having de Sitter vacua or classical de Sitter vacua with d smaller than 4, do you have anything to say about d equal 2? Actually, that's pure ignorance on my side.
Yes. I worked on it a little bit, but not from a string theory point of view. What I can just say is if you compactify the standard model, okay, say on an S2, you can have the Sitter 2. But the thing is that this Sitter 2 will anyhow be unstable. This you can show. And secondly, if you nonetheless don't want it to be there, which I think is very reasonable to ask, that you don't even allow the unstable ones, you can actually constrain the fine structure constant, okay? The time variation on the fine structure constant. So what we showed there in this paper with Venkin and Montero is that there is a super nice consistency in all of these swampland conditions. So not having a two-dimensional de Sitter really makes that fine structure constant get not vary too much in time, consistent with observations. No. But I haven't looked at this string theory compactifications.
Thanks a lot.
More questions?
I mean, I can ask a question just out of curiosity. If you don't believe in this Sitter, would you believe string theory doesn't describe our universe, or would you believe in quintessence, or would you believe there's something else?
Yeah, that's a good question. So this is exactly why I started my slides with the non-Bunch-Davies vacuum. Okay, there are two ways. So let me not even discuss string theory. What I was trying to say that even in effective field theory is a bit. I mean, you have to do some effort to get a fully constant de Sitter space, right? So you have to argue that the Euclidean vacuum is the right one, which, for instance, for a black hole is not, unless I put it in ADS or whatever. And does that violate observations? Not at all. Not at all in any obvious way. Why? For instance, in these discussions about non-Bunch-Davies, you really typically, when you do a typical computation, the effects are too small to observe. Okay, the equation of state parameter would be very close to -1 and perfectly consistent with current data, right? Does that mean it is quintessence? Yeah, when you want to think everything in terms of classical physics, then okay, the easiest thing is like thinking of this as a scalar field rolling down. But I'm not sure whether you should always classicalize everything. So I'm unsure whether we should think of this as quintessence.
Okay, so any more questions?
I have a very nice question, Thomas.
Yeah.
Thanks for this great overview talk, by the way. So normally in the context of swampland and all these things, we think of lambda arising as an effective field theory parameter from some UV complete setup. but as you said in the beginning, lambda can appear dynamically. Like in our universe, when you go to the very Big Bang time, you won't expect any effective field theory like description anyway. There could be some weird microstate like description, and lambda can emerge from dynamically from there, right? There could be a dynamical mechanism for generating lambda rather than. So could you make some more comments on this? Because I thought you had something like that in mind, but if you can elaborate.
To be honest, it's difficult to elaborate exactly because it's so difficult. So the only thing I can mention is something that I actually said, which was emphasized in a paper by not by me, by Ulf Danielsson, which is called the quantum swampland. Is just saying, okay, the arguments in the swampland for maybe the non-existence of the Sitter space, maybe they are not so different from all debates about the choice of vacuum in the Sitter space and whether it backcorrects and you get an RG flow. But yeah, it's really hard to make it any more precise. As you say, you would like to maybe have a microscopic description. The only thing I can maybe add there is some people say, well, a holographic description might really help. And I would agree. And what I find very appealing is that the only holographic descriptions, which I think are sort of convincing, are the ones coming from Aninos et al., which are like higher, they come from higher spin gravity, okay? And the weird thing with higher spin gravity is that this is the example of a sort of quantum gravity theory, quote unquote, that violates all swampland conditions. And the reason it is that it doesn't come with a massive tower, okay? So all fields in Vasilyev's higher spin gravity theory are below the Hubble scale, right? So in that sense, it is not consistent with swampland conjectures, but we are totally fine because the thing we assume is that we always have Einstein gravity, and Einstein gravity is always UV completed with massive towers. So I don't think there's a clash, for instance, between the DSCFT proposals, which you could think of as a microscopic description, and the swampland conjecture that maybe there's no de Sitter space.
Thank you very much. Thanks.
Any more questions? Okay, so if there are no more questions, then let's thank Thomas once again.
Thank you.
And with this, this day, very lively day comes to an end. So we will meet tomorrow again at 9 o'clock. So unless the organizers have something to say, we can end here. Well,
yeah. Thank you, Vindu, very much for sharing this, and thanks to all the speakers for the amazing talks. And please do join Slack. We can continue this on Slack. So my earnest request would be, please do that, and also send the slides as soon as possible. Thank you very much. See you tomorrow. And have a nice day, rest of the day.
Bye.